Hello, this is Mrs. Snook with section 2.4, complex numbers. And in this video, we're going to use the imaginary unit I to write complex numbers. We're going to add, subtract, and multiply our complex numbers. We're going to use complex conjugates to write the quotient of two complex numbers in a standard form. And we're going to find complex solutions of quadratic equations. So before we get started, let's talk about the imaginary unit I. I is defined as the square root of -1, and that's the imaginary unit. And that opens up a whole new number system apart from real numbers called complex numbers. And a complex number just means that it has an imaginary part. And we often write it in standard form a plus bi, where a would be a real number, and b is a real number, but bi is imaginary. So think of it as a real plus an imaginary. Believe it or not, the ancient Greeks knew about complex numbers, but they didn't see any use for them, so they didn't pursue it. But lucky for us, complex numbers have come back, because without complex numbers, we wouldn't have the entire branch of electrical engineering, which means you would not have cell phones. So every time you look at your cell phone, be thankful for complex numbers. All right, so let's start with adding and subtracting complex numbers. And we're going to write our answer in standard form. That means a plus bi. If you look at our first one, we have 3 minus I plus 2 plus 3i. Just combine like terms. So I have a 3 plus 2, that's 5. I have a negative I plus a 3i, which gives me plus 2i. That's done. That's all you got to do. So that's addition. Subtraction is right here, and remember, distribute that negative. And then we get I plus 2i minus 4 minus 2i. Now combine your like terms. My 2i's drop out, so I have a -3. No need to say plus 0i. You can just leave it as -3. So this is a case where the imaginary part actually dropped out. So even though we were subtracting complex numbers, we got a real number as a result. Now look at this next one. We're doing a subtraction and then an addition. So just like before, distribute that negative. So 3 plus 2 minus 3i minus 5 minus I. Now we're going to combine our like terms. 3 plus 2 minus 5, that all drops out. And then I have a -3i minus I, that's going to give me a -4i. So there's our answer there. So this is one where all the real parts dropped out. Now look at this one. We're adding and then we're subtracting, so distribute the negative. So 3 plus 2i plus 4 minus I minus 7 minus I. Well, I have a 3 plus a 4 minus a 7, so those drop out. I have a 2i minus I minus another I, so those drop out. Everything drops out, so our answer here is 0. All right, next one is multiplying complex numbers. This works the same way as when you're multiplying polynomials. So just think distribute. So I have 5 times -2 plus 3i. I'm going to distribute that 5. That gives me -10 plus 15i. And I'm done. Now on the next one, I have 4i times -1 plus 5i. So distribute that 4i. That gives me -4i plus 20i squared. Now remember, I said that I is the square root of -1. So we have -4i plus 20 times square root of -1 squared. Well, when I square a square root, those are inverse operations. They undo each other. So what I end up with is negative 4i plus 20 times negative 1. So for that reason, I don't want to see any answers with an I squared in them because that simplifies to negative 1. So this one is negative 20 minus 4i. Make sure you're simplifying. Next one, I have 2 minus I times 4 plus 3i. So distribute just like you do with polynomials, or you can think of it as FOIL, where you do your first, outside, inside, and last. I think distribute, so I'm distributing the 2, so I get 8. I distribute the 2 again, so I get 6i, and then I distribute negative I, negative 4i, and I distribute negative I again, negative 3i squared. If you FOIL, you get the same thing. And then we are going to simplify and combine like terms. So I have 8, I have plus 6i minus 4i, that gives me a plus 2i. And then I have minus 3i squared, so that's minus 3 times negative 1. And then simplify again. My 3 times negative 1, that equals 3, plus 8 is 11 plus 2i. And now we're done. Next one, I have 3 plus 2i squared. So that's going to be 3 plus 2i times 3 plus 2i. Make sure you write it out. The temptation is to just square your first and last term. But if you do that, you're going to miss this middle term that you're going to have. So make sure you write this out and then distribute. 3 times 3 is 9. 3 times 2i is 6i. So that's my first term. Second term, 2i times 3 is another 6i. 2i times 2i is a 4i squared. So I get 9. Combine like terms, so plus 12i plus a 4 times a negative 1. That's going to give me 5 plus 12i. And that one's done. Our last one, I want you to look at this one. Notice how the first term on both of these complex numbers is 3. And notice how the second term on both of these, the imaginary part, is 2i. And then you see how you have a plus and a minus? So right here was a plus, right there was a minus. That's actually the only difference between those two terms, is that plus and that's minus. That's called a complex conjugate. And when you multiply a complex number by a complex conjugate, something very interesting happens. So let's go ahead and distribute and see what happens. Matter of fact, pause your video here, distribute, and then come back and compare your work with mine. So pause the video now. So if you distribute, what you should have seen is that that middle term, the negative 6i plus 6i, that drops out completely. And then when you have an I squared, remember, substitute in negative 1, so your answer is all real. That's very useful because in our next operation, when we divide, we don't really want imaginaries in the denominator. So we're going to use this property of the complex conjugates to make our divisions easier. So before we do that, we're going to practice just multiplying by the complex conjugate. So that means first you need to identify what the complex conjugate is. So take your real term, write that down. Take the imaginary term, write that. Look at your operation, it was adding, so it was a plus, make that a minus. That's all you got to do. Now you've got your complex conjugate, and so now just distribute. So 1 minus I plus I minus I squared. So check that out. Those i's drop out. I get 1 minus a negative 1. which is 2. Now try this one. Write your first term, write the last term, change that minus to a plus. Now you've got your conjugate and you're ready to distribute. 9 plus 15i minus 15i. So you can see those 15i's are going to drop out. Minus 25i squared. Those drop out. So I get a 9 minus 25 times the negative 1. That's actually 9 plus 25. And our answer there is 34. Okay, so now we're going to use that property that lets us make the imaginaries drop out to do a quotient, to divide. So what we're going to do is I'm going to multiply the numerator and the denominator by the conjugate of the denominator. So that's going to be 4 plus 2i. 4 plus 2i. And what that's going to do is that's going to make the denominator all real. And since numerator and denominator are the same, I'm not changing the value of my expression at all. I am multiplying by 1 in a form that allows my denominator to go real. So here we go. Let's do the denominator first. So 4 times 4 is 16. 4 plus 2i is 8i. Negative 2i times 4 is a negative 8i. Negative 2i times positive 2i is negative 4i squared. And then do the same thing in your numerator. 4 times 2 is 8. 2 times 2i is 4i. 3i times 4 is 12i. 3i times 2i is 6i squared. All right, my 8i's drop out. I get a 16 minus 4 times the negative 1. That's my denominator. My numerator, I have 8. 4i plus 12i is 16i. And then plus 6 times negative 1. So 8 plus the negative 6 is 2 plus 16i. That's our numerator. Denominator is 16 minus negative 4. That's 20. Now notice that I can pull a 2 out of each of my terms. So I'm going to reduce this a little bit. I'm just going to pull a 2 out. So I get 1 plus 8i divided by 10. And I'm perfectly fine if you stop right there. I think your book goes an extra step and they make this 1 over 10. And then they reduce the 8 over 10i to 4 over 5i. That's okay too, but I'm perfectly fine if you want to stop right there. All right, so now we're going to write complex numbers in standard form. So we have a negative square root of 3 times the negative square root of 12. So let's rewrite this. Negative square root of 3, that's the same thing as I times the square root of 3. I pull that I out because I is square root of negative 1. And that's times I square root of 12. Outside times outside. So I get I squared, inside times inside, square root of 36. Square root of 36 is 6. I squared is negative 1. So I get a negative 6 as my answer. All right, next one. Do the same thing. Pull I out. So I get I square root of 48 times, no, not times, minus I square root of 27. Now, right now, at first glance, this looks like I can't go any further because I have I root 48 minus I root 27. But let's simplify those square roots to see if we have common terms. So 48 That's a 16 times 3. So I'm going to square root my 16 to pull that out. So I get 4i square root of 3. 27 is a 9 times the 3. So I can square root that 9, pull that out, so that becomes a 3. So I get a 3i root 3. Look at that. The square roots are the same. So those are like terms. So 4i root 3 minus 3i root 3 is 1i root 3. And that one's done. All right, this one. We are squaring a complex number. So you need to rewrite this. -1 plus I square root of 3 squared equals -1 plus I root 3 times -1 plus I root 3. And now FOIL this out. So 1 minus I root 3 minus another I root 3 plus I squared. Root 3 times root 3 is just 3. So I get 1 minus 2I root 3. And then I squared is -1 times 3 is a -3. Combine like terms again. -2 minus 2I root 3. And we're done with that one. All right, the last idea we have is complex solutions of a quadratic equation. So if you look at the first one, x squared plus 4. Well, that's a sum of two squares, which means what I've actually done is multiplied by a complex conjugate. So I can factor this. X plus 2i, x minus 2i. So when you do that, what you end up with is x squared plus 4. Okay? So then this one, x plus 2i equals 0, x equals -2i, x minus 2i equals 0, x equals 2i. When you have a sum of two squares, think about complex conjugates. Some people, when we did difference of two squares, were wondering why it didn't work with a plus. And I told you because it goes complex. And this is why. If you actually FOIL out our complex conjugates, that's going to bring you back to x squared plus 4. Now, how do you find those conjugates? Just take the square root of both terms. So x and 2, and then 1 plus and 1 minus. So it's just like a difference of two squares. All you got to do is make sure that you're going to be complex. So you need to put in the I. All right, next one. We can't factor that. So what we're left with is quadratic formula. So if you remember, that is x equals opposite b plus or minus square root b squared minus 4ac all over 2a. So remember your quadratic formula. A is the 3, b is your -2, c equals 5. It's already set to 0, so I'm good to go. So now just plug in. So opposite of b, that gives me +2, plus or minus square root b squared, so -2 squared, minus 4ac, so 4, a is 3, c is 5, all over 2a. I just plug in, and I get 2 plus or minus square root of 4 minus 60 over 6. That gives me 2 plus or minus square root of -56 over 6. Remember, pull that I out. So I get 2 plus or minus I root 56 over 6. Now let's see if we can simplify square root of 56. Well, 56 is 2 times 28. 28 is 4 times 7. So right there, I have a perfect square. So I can pull out that 4. That's square root to 2. So I get 2 plus or minus 2i. Left under the radical is the 2 times 7, or 14. Divide by 6. And now look again, I have all even numbers, so I can pull out a 2 everywhere. So I get 1 plus or minus I root 14 over 3, and I'm perfectly fine if you leave your answer like that. So that's it for today's video. Thanks for watching and have a fantastic day.